mean by that? Well, these external interactions with the environment, they're always there, but we assume they're very weak, so we can neglect them. Okay, so these are isolated many-body quantum systems. So before talking about time scales in these isolated quantum systems, I have to tell you first what we mean by relaxation in these systems. Since they are isolated, they're just described by quantum mechanics, Schrödinger's equation, linear dynamics. So what do we mean by equilibration or relaxation here? You pick an observable, let it evolve, and after some time you see just fluctuations around an asymptotic value. That's what we are calling equilibration. But let me be more quantitative here. So this is the equation that describes the evolution of our operator, right? Let me call alpha the eigenstates of the Hamiltonian that evolves the system, E is the eigenvalues, and these C's here are the overlaps between the initial state and these eigenstates, the energy eigenbases. So you see that, well, if I write these evolved states like this, in terms of the eigenstates, you see that the equation for the observable has two terms. This first term here is when alpha and beta here, they are equal. So this is a time-independent term. This is the asymptotic value. So this is the infinite time average, the saturation point. We are studying finite systems, so that's why the dynamics has to saturate at a finite value. This other term is the one that determines the dynamics, controls the whole dynamics, and will lead, after a long time, it will lead just to these fluctuations. We know that these fluctuations are very small because we are dealing with many body quantum systems, so very complex. We don't have many degeneracies. We are dealing with states that are chaotic. We are dealing also with a system that is taken very far from equilibrium, so these coefficients here are very small. So these fluctuations are very small. We know that, and we've studied them well with Pastavsky. And we know that they are small and that they decrease exponentially with system size. So that's what we are calling equilibration, the fact that for most time, the observer will be there at this asymptotic value, okay, around this point here. An interesting question is, well, how about this asymptotic value? Can we call it a thermal equilibrium? So the idea is, this infinite time average, does it agree with a thermodynamic average? Like something that we would get by using a standard statistical ensemble, so a microcanonical ensemble. If we have this agreement, that's what is called thermalization. Probably Israel told you about it last week. And what is the guarantee that this will happen, that this equality will hold, if we have quantum chaos, or if you want to say ergodicity. So I'm not going to talk about thermalization here or equilibration. These are ideas that we have some consensus about. What we are interested in is in the timescales to reach equilibrium. Okay? And this is a point that is not so well understood yet. There are many, many studies about equilibration and thermalization, not so many studies about the timescales. And the ones that exist are a bit contradictory. Some studies say that it will take longer, that the time for equilibrate increases as the system size increases. Others say that it should decrease as the system size increases. Okay? And many of these studies are based on abstract mathematical models. So what we decided to do, well, let's pick a realistic system, a system that is studied experimentally, and let's see what are the time scales there, dealing with real initial states. Okay? And what we find is that there are different behaviors at different time scales. So if you focus just on one of these time scales, you may reach wrong conclusions. So I'm going to describe these different behaviors at different time scales, and then I'm going to focus on two very long time scales. One is the Thouless time, so I'm going to tell you what we mean by Thouless time in a system that has interaction. And the other one, even beyond the Thouless time, is the relaxation time, is the time to finally reach that asymptotic value. Okay? What we found is that both increase exponentially with system size. So let me just give you the main results before we move to the results, to the description of the results. So we have two very long time scales, not just one, the Thouless and the relaxation time. Both increase exponentially with system size. What happens, so first I'm going to start describing to you what we have when the system is chaotic. So if you prefer, you can substitute the word by ergodicity. And then what happens when the system leaves the chaotic region and approaches a localized phase. And what we see there is that these 2 time scales remain, but the Thouless time gets longer and longer, closer and closer to the relaxation time. Okay? We have the description for the entire dynamics, and not just numerical results, also some analytical estimates. To give some motivation, non-equilibrium quantum dynamics and thermalization, they're not just theoretical questions. There is a lot of experimental interest. So just an idea of some of the experiments that are out there. There are many experiments. Well, non-equilibrium quantum dynamics has been studied for a long time in NMR. No? So they apply magnetic fields, polarize the system, no? the nuclear spins, turn it off, and then study the dynamics. The big sensation at the moment are those experiments with cold atoms and ion traps, because they are highly controllable. So they can control the strength of the interaction, the level of disorder, play with different geometries, 1, 2, 3D. And the systems are very well isolated, so you can study coherent evolutions for very long times. What is fascinating also about the ion traps is that they can tune the range of the interaction. So they can have interaction very, very far away also. Okay? Many of these experiments can be described with models of spins half. No, they are not exactly made of spins half, but they can be modeled with spins half, and these are the systems, the models that we'll be playing with here. Now, one-dimensional systems of spins half. So let me give you an idea about the Hamiltonians that we deal with. So in the Hamiltonian, we have terms such as this one. So sigma Pauli matrices. So this term here, XX, YY, what it does is the following. When it sees a state like this, with a spin up and the other one down in the z direction, it flips the spins. Flips the spin, so it brings the spin up from a site n to a site n plus 1, because we have just couplings between nearest neighbors. So it moves this spin up, or this excitation, along the chain. It's a term of kinetic energy. You can also write it in terms of creation annihilation operator. There is a mapping between spin operators and these boson operators. So this is just a hopping term. The other term that shows up is a term of interaction, the ZZ term, which is the easy interaction. What this term is telling us is that states where the spins are parallel have different energy from states where the spins are anti-parallel. Okay? And again, I can write this with creation annihilation operator, so this is the term of interaction. This Hamiltonian here, where I have just couplings between nearest neighbors, and it's one-dimensional, is an integrable Hamiltonian, meaning you can solve it with a method known as beta ansatz. We're going to add one more term to this Hamiltonian, which is this one. So the sum of sigma z's. So what this term means is that we have on-site disorder. These HNs are random numbers in a uniform distribution between minus h and h. So what this term means is that on each site we have a different Zeeman splitting randomly distributed. So this is a term of on-site disorder that can bring the system into the chaotic domain. I'm going to tell you more about what we mean by quantum chaos. Let me just say that we don't really need disorder to have chaos in these systems. Just a single defect, a single Zeeman splitting, so that's what I'm putting here, just a single one different from the others with a fixed value is enough to bring us to chaos, okay? But we are going to be dealing with this Hamiltonian that has also on-site disorder. So let me tell you a little bit about what we mean by quantum chaos, and let me start saying a little bit about full random matrices. So these are the matrices that Wigner used back in the 50s to describe the spectra of heavy nuclei. So instead of going for the details of those interactions, let me just fill this matrix with random numbers. And the only constraint is that it should satisfy the symmetries of the system that we are studying. So for example, a real and symmetric matrix. So these random matrices have interesting properties. For example, pick all of the eigenvalues, and let's look at the histogram of the neighboring spaces, E2 minus E1, E3 minus E2, and so on. Pick all that and make a histogram. You see that it follows this red distribution, which is known as Wigner-Dyson distribution. So what it's telling us is that there is no spacing very close to 0. These are for full random matrices. Well, this is also what we find when you're dealing with heavy nuclei. It's also what we find when we are dealing with our chaotic spin models, what I'm calling chaotic spin models. So remember, this is the Hamiltonian we are dealing with. this chaotic region shows up when the disorder strength, this H, is of the order of the coupling parameter. If this disorder is not there, that's what I said is an integrable point, so we have distributions that look like this one, a Poisson distribution. There is another region where we get a Poisson distribution, is when this H starts becoming very large and dominates. Now it becomes much larger than this part of the Hamiltonian. So we reach another integrable point, which is localization in space. Okay? So chaotic region, when they are of the same order, we are going to study this region. We can substitute the word chaotic by ergodic, as I said. And we are also going to study what happens when the disorder starts increasing and I'm between these two regimes, no? When we break ergodicity. Okay? So I'm saying that these systems are chaotic, but I didn't really told you what we mean by chaos, right? So there is a classical, a quantum classical correspondence between, for one-body systems, there is this quantum classical correspondence between this kind of distribution in the quantum domain and chaos in the classical domain. No? You study the trajectories in phase space and find Lyapunov positive Lyapunov exponents in the classical domain. So there is this quantum classical correspondence, well understood, well studied numerically and semi-classical studies for one-body systems. Here we are studying many-body systems. No? So this quantum classical correspondence is not so well established. I'm just extending the term. But this is a very hot topic at the moment. Another thing that is important to say is we are saying that the level statistics of our real models are very similar to what we find for full random matrices, but of course there are differences between these two cases. And where are the differences between these two cases? No? So let me repeat again what a full random matrix is, just matrices filled with random numbers, no? Much bigger than what we have here, like 20,000, but just filled with random numbers. Our spin systems, our realistic models, the matrices are very, very sparse. So of course there are differences, and where do we find these differences? Okay. For example, if you look at the density of states of full random matrices has that usual semicircle shape. In our real systems, many body systems, we have just two body interactions. In that case, the density of state is Gaussian. Okay, so there is a big difference already here that will affect the dynamics. Another difference shows up at the eigenstates. The eigenstates of full random matrices are just random vectors, no huge superpositions where these coefficients there are just random numbers. There are ways to study how big these superpositions are, no? How much delocalized the states are. One of these quantities is the participation ratio. So you write your eigenstate in a certain basis. The participation ratio is 1 over the sum of those coefficients to the fourth. So if the state is very localized in this basis, you have very few C's. Very few C's, so small participation ratio. If the state is a huge superposition, very much delocalized, you have many, many, many tiny C's, and this number will be very large. For full random matrices, all of the eigenstates, what I'm showing here is the participation ratio for each eigenstate. All of them are completely delocalized, no? So the participation ratio is proportional to the dimension of the Hilbert space. So they are all random vectors. They're all equivalent kinds of states. If you move to a real system, the story is different. No? It's close to the middle of the spectrum that the states are very much delocalized. Even there, they are not really random vectors. They're close, but not really there. As you move to the edges, the states are pretty localized. And the results now for the participation ratio also depends on the basis. Okay, so this is very important for dynamics. No? This energy dependence will affect the dynamics. Yes? It is increasing here, but the system is finite, no? So if it is infinite, it would just be increasing forever. But the system here is finite, that's why you have both bounds. At the tail here, there is a signature of Okay, okay, you tell me then. Okay, fine. But you tell me later then. Okay, so then let's move to the dynamics. Remember, we are dealing with the entire Hamiltonian. What are the important parameters here? H, no, this minus H to H. So H is the strength of the disorder. So this is an important parameter. The other important parameter is L, which is how many sites we have. We are going to assume that half of the chain has spins pointing up, and the other half has spins pointing down. So this means we'll be dealing with a very big Hilbert space. Okay? We are going to prepare this system in initial states such as this one, spins up and down in the z direction. If you don't like the language of spins, you can think about particles. No? So on each side, you either have a particle or no particle. And then we'll let this state evolve according to this whole Hamiltonian here. This is a scenario of very strong perturbation. Why do I mean very strong perturbation? This initial state is like an initial state. It's like an eigenstate from this part of the Hamiltonian. But we let it evolve according to this whole Hamiltonian. So this initial state is very different from any eigenstate of this Hamiltonian. So very, very strong perturbation. This is important for the dynamics again. In this limit of very, very strong perturbation, the energy distribution of this initial state has a shape very similar to the density of states. Again, it will be Gaussian. I'll come back to this, but this is important, okay? So I have an initial state that is very much spread out in the energy eigenbasis. So the dynamics initially will be explosive, super fast. And we studied the entire dynamics, as I told you. Many averages, big averages, averages over initial states, averages over disorder realizations, okay? And, but not just numerical results, we also have some analytical estimates that match these results extremely well. Okay, so there'll be two things that we'll be doing here. First, what I just told you, I'm going to pick this initial state and let it evolve according to the whole Hamiltonian. Fine, this is very realistic, what people can do in the labs. But we are going to do another thing, which is the following. We are going to let the system evolve according to full random matrices. So remember, these are matrices filled with random numbers. We are going to assume that the diagonal gives us the initial state, and we let these initial states evolve according to this whole crazy matrix. No? So it's completely unphysical. No? There are no systems entirely described by full random matrices. Now, if you have all the matrix filled with random numbers, that means that all the particles are interacting at the same time. So that is unphysical. But what is the big advantage of dealing with them? Well, the main advantage that Wigner already had realized, now you can get analytical results. Now, we are just dealing with random vectors and eigenvalues that are very much correlated, so we can get analytical results for the dynamics, which I can then use to compare with the results for the real system. Okay? Okay. So the quantity that I'm going to show you results for is this quantity here, survival probability, not just the probability for finding my initial state later in time. So an overlap between the initial state and the evolved state. I'm going to show this quantity because it's easy to explain, and we have analytical results, but we have results for many other observables, such as the spin autocorrelation function. This is a quantity that is measured experimentally. I'll show to you some plots for this quantity later. What is interesting is that at long times, the behavior of the survival probability and of this quantity are pretty much comparable. Let me remove this from here. Okay, so let's have a look at the equation for this survival probability. I'm going to do the same thing that we did before, write the evolved state in terms of the energy eigenbasis. So you see that the survival probability will be just the sum of those components, the sum of those overlaps with those faces. Let me open this square here, as we did before in the beginning of the talk. So you see that we have two terms. This first term, when alpha and beta are different, is the one controlling the dynamics. This is when alpha and beta are equal, is that term, the infinite time average, the time-independent term. So I put a bar here to indicate is that saturation value. Okay? Let's start studying the chaotic region when the disorder is of the same order of the coupling parameter. So remember, chaotic region means eigenvalues that are very much correlated. Now, they are so much correlated that the spacings are never close to 0. No, we have no spacings close to 0, so the levels do not cross. I have no degeneracies. They repel each other, so I have a spectrum that is rigid. Eigenvalues very much correlated. Okay. How about the eigenstates? It's just the opposite. These coefficients here are pretty weakly correlated. No, so uncorrelated is too much, but pretty weakly correlated. We are dealing with eigenstates that are big superpositions. Okay. Well, to be more technical, they fill the energy shell. Okay, so that's how we start. This is the entire result for the survival probability. We start at 1, go through the whole dynamics, and then finally saturate at that infinite time average that I mentioned before. This value here is very small because we have very strong perturbation, because my system is chaotic, so I have a whole bunch of tiny, tiny C's. Now, my initial state is very much delocalized. So this infinite time average here is inversely proportional to the dimension of the Hilbert space. Okay, tiny value. Okay, what do we have in between? I'll just say, and then we'll go for the details. Initially, very fast Gaussian decay. Remember the energy distribution I said is Gaussian? Well, now we are getting a Gaussian decay. It slows down, gives us a power law behavior, and then it reaches this minimum value here, which is even below the saturation point, and then it goes up and finally saturates. Okay? This is for a realistic system in the chaotic region. The top here is the result for full random matrices. Let me bring it down so you can see it better. This is the result for the full random matrix, which I said is unphysical. What we have initially is a behavior that is different from what we have there. No? This initial behavior is described with a Bessel function. So you see these oscillations that also decay as a power law, but with an exponent that is larger than there. So the initial behavior is different, but later we have that same dip. No? This dip is caused by correlations between the eigenvalues. This dip is very similar for random matrices and for realistic systems. So it's at this point, long times, where the behavior is becoming pretty similar. Okay, so now I'm going to go step by step. Okay. So this is the expression, again, for the survival probability. I'm going to substitute this sum with an integral. So this rho that you're seeing here is a function that carries this delta function. So I can go back to the sum if I want. So it's a sum of delta functions. Sum of delta functions is density of states. But we have an extra term, which are those components of the initial state. So this thing here gives us an energy distribution, but for that particular initial state that we picked. So this is known as not as density of states, but local density of states, because it depends on the initial state that we picked. So you see that if I know this distribution, I know the survival probability. I just have to do a Fourier transform. So we are going to study a little bit this distribution. But let me start removing those C's. Okay? So this distribution here, without the C's, is just the density of states, and we already talked about this. For full random matrix is the semicircle. For the real system, Gaussian. Let's put the components there. What changes? Okay, so now the components are there. Well, for the full random matrices, again, just the semicircle, nothing changed. For the spin model, you're seeing a Gaussian there also. But, well, let's see what are the conditions for this Gaussian to show up. As I said, this Gaussian shows up only when we have very strong perturbation. Okay? Imagine if I had taken an initial state that was very close to one of the eigenstates, the distribution would be very narrow. Okay? As I increase this perturbation, then this narrow distribution would get broader and broader. Eventually, we reach a Lorentzian, Bright-Wigner. That's the regime of the Fermi-Golden rule. But if we go even beyond that, then we finally get this Gaussian. Okay, so this Gaussian is in this limit of very strong perturbation. There is another catch here. We are looking at initial states that have energy close to the middle of the spectrum. If I would pick an initial state with energy close to the edge, then I get a skewed Gaussian. Okay, so you see that there are many factors for this real system. But once I satisfied all this, very strong perturbation, energy close to the middle of the spectrum, then this Gaussian shape is general. Okay? For many body systems with two-body interactions. So what do we have to do now? the Fourier transform that we mentioned before. Fourier transform of this semicircle gives us a Bessel function of the first kind, and that's what you're seeing here. Fourier transform of a Gaussian gives us a Gaussian. That's what we're seeing here. So this gamma that shows up there is the width of this energy distribution. So this is our first important time scale, 1 over gamma, no? Is this decay of this initial state. But I'm not showing long times here. Let me show to you what happens beyond this time. So if I study that result for the Bessel function at long times, you see that the behavior is power law with exponent 3. So this is what we have here, now these big oscillations, and the decay, the envelope of these oscillations is power law T2 minus 3. This exponent is determined by how we approach the bounds of the spectrum. No? In this case, it goes abruptly, and that's what gives us this big exponent here. No? So the power law decay is caused by the bounds in the spectrum. How about the spin model? In the spin model, we go to the bounds slowly, following this Gaussian tail. So the exponent here is 2, is smaller than that one. No? But we still have this power law decay here. Maybe it's not too convincing here because we have a small system size. But let me show this to you. We went to much larger system sizes, and then things become more obvious there. That power law behavior for the spin system, you can also see directly from the Fourier transform. Now, if you take into account that there are bounds, when you do the Fourier transform of the Gaussian, you get Gaussian decay together with an error function. And if you study this asymptotically, you get power law with exponent 2. Okay? All right. So we understood this beginning. It remains to understand the dip. So we understand that this beginning is not universal. It depends on the shape of the energy distribution. Now here it was Gaussian, here was the semicircle, so you see that the behaviors are different. But that dip is pretty similar to both cases. Where is it coming from? When we are studying the dynamics, we cannot focus only on the envelope of the distribution, because the system is not continuous. We have a finite quantum system, so the spectrum is discrete. So we also have to take into account what is inside this distribution. So we have discrete levels, and in the chaotic case, these levels are very much correlated. The fact that we have correlated eigenvalues is what causes this dip. This dip is known as correlation hole. Okay, so it's a reflection of the presence of correlated eigenvalues. It takes time for it to show up, because it takes time for the dynamics to realize, so it takes time because it takes time for the dynamics to realize that the spectrum is discrete. Okay? This hole is a direct manifestation of level repulsion that we have in the dynamics. Fast behaviors that we have before the correlation hole, Gaussian, exponential behaviors, they're just reflection of strength of the perturbation. The hole is the true signature of level repulsion. Okay? Now, this hole was studied before in random matrices, not in this context of dynamics, just as studies of correlations between the eigenvalues. No? So they would do the Fourier transform of this spectrum and study what I'm calling correlation hole. The function that describes that dip is this function here. And what we decided to do is, well, since the level statistics for the real system is similar to the level statistics for full random matrices, let's use the same function to describe the dip for the real system. Okay? So the argument is a little different because it depends on the distributions that we have, but the function that we are using is the same. Okay, so I described to you all these little pieces. Let me now put everything together in one equation, starting with the full random matrices. No? So this is the whole equation to describe the entire dynamics. What we have, the Bessel behavior, then the hole, and then the saturation. So this is the entire equation, putting all of those pieces together, or you can go directly and derive that analytically by studying this expression that I gave to you before. We have this derivation if you want to see. Okay? So this is the entire equation. Let's compare it with the numerics. In red here, we have this entire analytical expression. In black, we have the numeric. So you see perfect agreement. It's an analytical result, excellent agreement. Now let's see what happens. So you see everything here, right? The Bessel with the power law exponent 3, the whole, and then the saturation. Let's move to the realistic system. Again, I'm going to put all those different behaviors in a single equation. So here, initially, Gaussian with power law, then the whole, and then the saturation. This is the entire equation, but we are dealing with systems that are finite, so small systems. And so for this to agree with our numerics, we are using one fitting constant, but it's just one, okay? And so this expression here is shown with these dots, these red dots, and black is the numerics. So you see this very good agreement. Very good agreement. This is a log-log plot. So we are going from times 10 to minus 2 all the way to 10 to 4, and we see perfect agreement here. Okay, so now that I have this expression, I can go on and try to find analytical estimates. Analytical estimates for what? What are the time scales that are missing in this story? The time to reach the minimum of the whole and the time to saturate. So this time to reach the minimum of the whole is what we are calling Thouless time. So let me explain to you why we are calling this Thouless time. In non-interacting systems, Thouless time is the time that it takes for the particle to diffuse through the sample. Okay? Now we have a system that is interacting, when all these particles are interacting. So what we are calling Thouless time, and this we borrowed from the studies with Israelov, this interpretation. What we are calling Thouless time is the following. We start with a many-body state, and this many-body state gradually spreads out in this many-body space. So I have a spin pointing up here on site 5, it goes to 4 and 6. Wait a little longer, it goes from 4 to 3, and so on. So it goes on spreading into this many-body space, and it does it gradually. Once it visited all of these many-body states in this many-body Hilbert space, that's when we reach the minimum. Okay? So this is the interpretation for what we are calling Thouless time. There is another technical reason why we are calling it Thouless time. I can tell for those who knows about level number variance and so on. Okay? Okay, now, with this expression, then I can find this time. Now, estimate for this time. How do we do that? Well, this time, this minimum, shows up when we have the crossing between these two functions. Because this one is trying to go to 0, and this B2 is carrying us up to saturation. So I study this one at very long times, which is the power law behavior trying to go to 0, and this one at short times, which is this initial linear increase. Put all this in the expression, do the derivative, and then you get the time for the minimum. Okay? Let me isolate this expression in the next slide. So this is what we have for the real system. For the full random matrix, it's similar. The difference is that the power law is 3. But the expression is similar. But the results are actually very different. Why? Remember this gamma, right? This gamma is the width of this distribution. For the real systems, this width is given by how many states are directly coupled with my initial state. Well, I made a plot here. So suppose I have this initial state, 1, 0, 1, 0. How many states are directly coupled with it? Few. From site 3, my excitation can go to site 2. This coupling here, it can go to site 4, so this coupling here. And from 1, it can go to 2, so this. So just 3 states. So my initial state in a real system is directly coupled with few states because I have just 2 body interactions. As a result, this width is proportional to the square root of the system size. Now, in random matrices, all states, the initial state is coupled with all the other states. That's the very unphysical case. So this width is proportional to the square root of the dimension of the Hilbert space. So you see the consequence of that, right? This time to reach the minimum for random matrices is just a constant. It does not depend on the size of the system. While for the real system, it does depend on the system size. So why do we have that? Because we have a many-body space, exponentially large space that we have to visit, but we have just the directly couplings of this initial state involves just L different states. You see what I'm saying? Huh? So I have an initial state that is coupled with very few states, and it has to explore this exponentially large Hilbert space. So that's why it takes an exponentially large time. How about the other time, the final relaxation time? Well, for this one, I only care about this term, because this one, it's already going to 0. No? So this is the one that is bringing us to the saturation point. So I studied this term at long times. It showed this power law behavior. So it's coming up to the saturation. So what we do is to select a threshold, this delta that you see there, a threshold to say, okay, we are close enough to saturation. Okay? And what we get is this time. No? So the time, the relaxation time, is given by this expression. And this relaxation time is the same for the chaotic real system and for full random matrix, because we only care about the B2 function, which is the same for both. And what do you see here? Well, the gamma, which is that width of the distribution, and D, which is the dimension, so the total number of states that I have. This width divided by all of these states is the mean level spacing. So the time that I got here is the inverse of the mean level space. It's just the Heisenberg time, as it should be. No, but the nice thing is that it came from those expressions that we have. Okay, so these are the analytical estimates. Then we can go on with the numerics. How much time do I have? Okay, so then I can explain a little bit about the numerics. So the numerical results for the random matrix, remember, the time to reach the minimum does not depend on system size. So here we are going from 1,000, dimension 1,000 to 100,000, and you see no difference. But the relaxation time, yeah, it increases with the dimension. And everything matches very well our estimates. Let's go for the real system. In the real system, as we said, both increase with the system size, no? The Thouless time and the relaxation time. Let's be more quantitative, and let's put this in a plot. So here I'm showing the time scales as a function of the system size. These red dots is the Thouless time. This line here is what we got from the estimate, and you see very good agreement. Remember, we're doing big averages here, no? So each point here involves huge averages, and we are dealing with very large system size. So numerically, this is very challenging. Okay, in green here, again, numerics are these squares, and the blue line is the estimate, and again, very good agreement. No? So the estimates are very good. Even if you were very skeptical about that expression that I gave to you, this confirms that that expression was very good. This is for the survival probability. Remember I said we have results for other observables. One is that quantity that is the spin autocorrelation function. What is this is, we are measuring how close my spin configuration is to the initial one. Okay, as I move in time, how close the state later in time is to the initial state, the configuration of spins. The behavior here, so this is that quantity, and this is the survival probability. There are some differences at short times, but at long times, that's what I was telling you before, the behavior is very similar. Now again, the Thouless time, there is also a correlation hole there, and the time for this minimum increases with system size, and the relaxation. The similarity is such that if we use the same analytical estimate, again, we have very good agreement. Okay, okay, so this is the part about chaos, the ergodic region. Now we identify two different time scales, and both increase exponentially with system size for the real system. What happens as we move away from chaos, no? As we break ergodicity? When I'm in the chaotic region, remember the eigenstates are very much delocalized. If I look at the participation ratio, remember the participation ratio is this quantity here, 1 over the sum of those components. So the participation ratio in the chaotic region is proportional to the dimension of the Hilbert space. Now what we are going to do is move away from this region. How? I'm going to be increasing the disorder so that the disorder will now get larger than the decoupling strength. No? So you see the value of the participation ratio will decrease because my eigenstates will get more and more localized in this basis, more and more localized in space. Okay? So as it decreases, there is this region here where the participation ratio is proportional to the dimension to a power, to this D2. This D2 is smaller than 1. No? And we get the value of this D2 by doing scaling analysis. Scaling analysis of this participation ratio for different dimensions. No? So we know what is value of this D2 for different disorder strength. Then we go for the dynamics. So this is again the survival probability. You see that I have red plots and green plots. Red is the region where I still have a good Wigner-Dyson. Green is when I'm between Wigner-Dyson and Poisson. So what you're seeing here, we still have a power law decay, but the exponent is getting smaller and smaller. As I increase the disorder, as H becomes larger and larger, the exponent gets smaller and smaller. The dynamic slows down. This exponent from the dynamics, no, from the power law decay, this exponent agrees with this D2. No? So this D2 is called the fractal dimension. It's telling us that our eigenstates are becoming fractal. And this D2 agrees with the power law exponent. Okay? Okay, this is an old work that we have with Shannon from 2015. Again, I chopped the plot here. You're not seeing what happens next. What happens next is the correlation hole. So here you have the correlation hole. H.5 is strong chaos. And as I increase the disorder, what you see is that the depth of this correlation hole is decreasing, and it's getting postponed in time. Let me isolate these panels, and then you can see it better. See, as the disorder increases, you see that the depth is decreasing, and we studied the depth, how it depends on the disorder, how we move, how this depth can tell us whether we are chaotic or localized. But what we are interested here is in time scales. No? So you see that the time for this minimum is getting longer and longer in time. So what do we see for the time of this minimum as a function of the disorder? Well, this is the relaxation time. The relaxation time is the Heisenberg time, the largest time scale of the system. And in red, we have this thing that we are calling Thouless time. And you see, as the disorder increases, the Thouless time is getting longer and longer and getting closer and closer to that relaxation time, no? Meaning the hole is disappearing. This ratio between the relaxation time and the Thouless time in non-interacting system is the Thouless dimensionless conductance. What we are doing is studying this ratio now for an interacting system, and we are finding similar results. In the chaotic region, this ratio is very large. No? We have time to spread in this many-body space. But as the system moves towards localization, this ratio is getting smaller and smaller and closer to 1. Same result shows up also for that spin autocorrelation function. Okay? Anyway, summarizing the stories that I showed to you here, we studied the entire devolution of these realistic systems, different observables, different behaviors at different time scales, and then we identified two, not just one, but two very long times. One is what we are calling Thouless time, and the other one, the relaxation, finally. The relaxation increased exponentially for whatever system we have, because it's just the inverse of the mean level spacing. So increased exponential for full random matrices for the real system. The Thouless time is a different story. The Thouless time, our interpretation is that time for the many-body space to spread, the many-body initial state to spread in this many-body space, and it takes an exponentially large time for it for the real system. For the full random matrix, no, this is automatic because we are coupled with all the states. So for real system, the Thouless time increases exponential with system size. For full random matrix, we cannot even call it Thouless time. It's just a constant there. And we also have these interesting results as we break ergodicity, as we move towards localization, this ratio gets close to 1. Okay, so Thank you for your attention. Discrete.